Okay, so this video is going to be about free body diagrams, and that's just a tool we use to model the forces that are acting on an object, kind of like you can see here on this slide. So let's go ahead and practice. And I would recommend that you have a paper out, like have your science notebook out, title it Free Body Diagrams, and then do these practices with me, because you can watch me do it and be like, oh yeah, that makes sense. But if you do it yourself, you'll be able to remember it better when you need to do it without me there to help. So take a minute, pause the video if you need to, get out your science notebook, write free body diagrams, and then do all these practices with me, okay? So this is a cool guy who is doing a flip or something over this trestle or whatever that is. So we are going to diagram the forces acting on this guy. A lot of the times my students think that the force of his flip or the force of his jump is acting on him, but in reality it's not. So let's imagine, I'm not sure how this picture happened, but let's imagine that he like jumped in the air and did a flip. That's probably not what he did, but let's imagine. Then the second his feet leave the ground, the force of him pushing on the ground is not acting on him anymore. He keeps flipping because he has inertia, tendency to keep moving if he's already moving, right? But that force of him jumping is not acting on him anymore the second his feet stop touching the ground. So let's go ahead and draw this. I'm going to draw it with you because it's not really fair if you have to, oh, whoops. I got to turn on my pencil, I guess. Here we go. It's not really fair if you have to actually draw it and I just get to look at the picture, so that wouldn't be fair. So let's imagine this is what the guy looks like. This is not a great drawing, but that's okay. Okay, so he's doing a flip in the air, right? And I told you the force of him jumping is not acting on him anymore. But a force that acts on us all the time while we're on Earth or on any planet would be gravity. And gravity pulls us down towards the Earth. So we're going to start the arrow at the guy, and we're going to point it straight down. We're going to label it with a big F for force and the little word gravity so we know what type of force we're talking about. Now, he doesn't have any forces acting on him side to side right now, but he does have a force that's pulling him upward. I'm going to use a small arrow pointing upward because the force pulling him upward is not as strong as gravity. We all know that guy's going to fall down because gravity is stronger than the forces pulling up. But the forces pulling up would be air resistance, because as he's falling through the air, he's hitting all these air molecules, and those air molecules are slowing him down a little bit. Kind of like if you jump into a ball pit at like the McDonald's play place or wherever. You hit those plastic balls in the ball pit, right? And they would slow you down a little bit. If it was a deep enough ball pit, maybe you could keep falling through it. You'd probably eventually stop, but that's because the plastic balls would stop you. Air molecules are kind of like that, but they can't stop you as fast as the plastic balls in a ball pit, right? So air resistance is the air molecules that he's pushing out of the way and running into as he falls. It's a small force, though. It's not enough to keep him floating. Otherwise, we would all be able to float, right? Gravity is a bigger force. That's why I drew a bigger arrow for gravity, okay? These are the only two forces acting on him while he is in the air. All right, that's kind of a hard one to do first. Let's try another one. Here we have a car that's speeding along the road, and let's go ahead and diagram the forces acting on this car. And I want you to draw it with me so that you can get some practice. And guess what I'm not good at? Drawing cars. So it's okay if your car doesn't look great, mine doesn't either. Here's my car, and it's going on the road. Okay, I'm gonna add some doors and windows, just for fun. Okay, there we go. So remember, this car is on Earth. So even though it looks like it's floating off my road because I have a bad drawing, it's not floating, right? It's pulled towards the Earth. So we're going to do the force of gravity, pointing straight down. Big F for force, little word gravity. Now, something that our flipping guy didn't have, but the car does have, is called normal force, and normal force is the opposite of gravity. So let's go ahead and draw that arrow pointing straight up. Big F for force, little word normal, so we know what type of force it is. Now, normal force is the force of the road pushing up on the tires of this car. And in fact, normal force is acting on me right now. I'm sitting on a chair. So normal force is the force of the chair pushing up on me. And it counteracts gravity so that I don't sink all the way through the chair, right? Normal force is acting on you right now too. If you're sitting, it's the force of the chair or the couch pushing up on you. And if you're standing, it's the force of the floor pushing up on the bottoms of your feet. So anytime something is not falling through the air but sitting on something like a table, a chair, the floor, normal force is acting on that thing, pushing up, okay? And we'll do more practice with normal force. But anyway, normal force and gravity are balanced. They balance each other out. They're the same. Now the car is also, it's driving forward. So we're going to call that applied force, because the engine is applying a force to get it going forward. I mean, really, it would be the wheels, but no need to talk about that. So big F for force, little word applied, the applied force of the car pushing itself forward, right? And then we have some forces that's slowing it down. They're not as strong as the applied force, though, but they're still there. So we have friction, and I'm going to do a kind of a small arrow because friction isn't that big. Big F for force, little word friction. Friction between the tires and the road, slowing it down a teeny bit. And then also we have the force of air resistance, which I already told you is the force of like the air molecules as you're falling or as you're like running, like moving forward, like this car is moving forward, it's pushing air molecules out of the way. And those air molecules, when it hits the car, are kind of slowing the car down a little bit, but not very much. So that's the force of air resistance. When this car hits those air molecules and those molecules slow it down just a teeny tiny bit. So we actually have two forces slowing down the car, right? But the applied force is bigger than those, so that's why the car is going forward. Okay, that one's also tricky. Luckily, we're going to do some more practice. This, I looked up something hanging from a tree, and this popped up on Google. It's a very sad picture. I think it's a My Little Pony in like a trap or something. So I'm sorry if you like My Little Pony. It's kind of a sad picture, but I used it because I think it's kind of funny. But yeah, it's sad. Anyways, I'm not going to try to draw the pony because I know I won't be able to. So I'm just going to draw the net that the poor sad pony is trapped in. And this net is hanging from a tree. So here's my tree branch. Go ahead and draw this with me. Now let's talk about the forces acting on this net hanging from a tree. Or it could be anything hanging. So first of all, we have the force of gravity. It's pulling it down. That's a pretty safe bet since we're on Earth. We know we've got gravity pulling down. Now we don't have normal force because the net is not sitting on the floor. It's not sitting on a table or a chair. But it is getting pulled up because it's not falling down. It's hanging, right? We're going to call that the force of tension. So I'm going to do an arrow pointing up, big F for force, little word tension. The tension of the rope holding it up is counteracting gravity. So the force of tension and the force of gravity in this case are balanced because the net is just hanging there and it's not moving up and it's not moving down. So we got gravity, tension, and then the net, we're going to imagine that it's not swinging side to side or anything. It's just sitting there. So we don't have any side to side forces. Just gravity pulling down, tension pulling up. Okay, now let's move on from that sad picture, that poor little pony. Okay, cheese. I love cheese, so I had to include that. This is a piece of cheese sitting on a table. So let's go ahead and do a practice with this. Draw your piece of cheese. Okay, and it's sitting on a table. So we're on Earth, so we know we've got gravity pulling down. That's a pretty easy one. Big F for force, little word gravity. And then, since it's sitting on a table, we know the opposite of gravity is normal force. That's the force of the table pushing up on the cheese, and it's counteracting gravity. So normal force and gravity are balanced. That's why the cheese isn't moving anywhere. It's just sitting there. Okay, and we're gonna assume that the cheese is not like sliding anywhere, like nobody's pushing it or anything, so there's no side-to-side forces. It would just be gravity pulling down, normal force pushing up, and they're balanced, so it's just sitting there on the table. Okay, I think I have one more practice. Oh yeah, So I looked up person pushing a cart and I came up with this weird picture. I don't know if this guy is like picking up his wife from the store or something. Anyways, since we're just going to talk about the forces acting on the cart, we only have to draw the cart. We don't have to worry about drawing like the guy pushing it or anything. So I'm going to go ahead and draw the cart going on the ground. And since we're on Earth, we can be pretty sure that we've got gravity. So big F for force, little word gravity, pulling down. And then the opposite of gravity is going to be normal force. So big F for force, little word normal. That is the force of the ground pushing back up on the wheels of the cart. And then remember, this guy is pushing the cart. He's pushing it to the right. So we call that applied force because he's applying a force. Kind of like when we did the diagram of the car. So big F for force, little word applied. And then there are some forces slowing this cart down, but they're really small forces, right? When you push a shopping cart, it's not that hard to push it usually, unless you have a lot of stuff in it. So the forces that are slowing you down when you're pushing a cart are pretty small. And so I'm going to draw a small arrow for this. One of them is friction, so big F for force, little word friction. That is the friction between the wheels and the floor, slowing it down a teeny bit, but not really that much. And then air resistance, we've talked about before. That's also a really, really small force in this case. And that is the force of the air molecules that the cart is hitting. Those air molecules are slowing it down just a teeny tiny bit, but really not very much. So we have two forces slowing down the cart, but the applied force is way bigger. So the cart is going to move forward. Now, normal force and gravity in this case are balanced. So it's not like the cart is going to start floating or sinking or something. It's just going to stay in the up and down direction. It's not going to move. It's only going to move side to side because those forces side to side are unbalanced. Applied force is bigger, right? Let's really quickly do a net force thing just to make sure you understand net force. Let's imagine that the force of gravity, let's say it's like 100 newtons pulling down. Since normal force and gravity are balanced, normal force would also be 100 newtons, right? So it's not going to move up or down. They're balanced. But side to side, let's imagine the applied force is like 250 newtons. And then let's imagine air resistance and friction. We've got like 1 newton of air resistance and 2 newtons of friction. Now I'm just making up these numbers, but in the up and down direction, 100 newtons minus 100 newtons is 0. So those are balanced. But in the side-to-side direction, we have 250 newtons to the right minus 1 plus 2, right? Because we have 1 newton of air resistance and 2 newtons of friction. So that's 3. So we got 3 newtons pulling it back to the left. Now 250 minus 3 is going to be 247 newtons in the direction of the biggest force. The biggest force is to the right. That's the way the guy is pushing, right? So 247 newtons to the right, that is going to be the net force. Sorry about my messy handwriting. It's hard to write with a stylus. Anyways, so those are unbalanced forces side to side, and that would be the net force there. So hopefully that was helpful, and good luck on the test.